I will introduce the Galton-Watson branching processes in this video. The Galton-Watson processes are also called simple branching processes. So either Galton-Watson or simple branching process. So that the ingredients is essentially a positive or non-negative integer random variable. So given is a non-negative integer distribution with a generating function P of S. That's the most essential ingredient. And I'm going to consider Z and J, two indexed random variables, a two-indexed array of random variables, where N and J are non-negative. Actually, N and J are non-negative integers, but really we're just going to go from 1. The interesting bits are going to be when N and J are at least 1. Let me put it this way: N and J are at least 1 integers. Okay, so these random variables are completely independent of each other across all indices, so they are IID, and again non-negative integer. Well, okay, we see that IID non-negative integers with this distribution. Okay, so I have a non-negative integer distribution. The generating function is P of S, and I have a doubly infinite, completely independent array of random variables with that distribution. And so I'm going to use them to draw a process or generate a process. I'm going to draw time going downwards and being discrete. So there is time 0, there is time 1, there is time 2, and so on. And I'm going to start with one amoeba. So suppose that there is an amoeba that starts at one individual. So I'm going to say that at time 0 I have one individual in this system. Z0 is the number of individuals at time 0. Okay, and this is 1. I fix that to be 1. Now between time 0 and time 1, this individual will have a total of Z11 offsprings. So maybe Z11 is 3, and so this individual will have Z11 offsprings. Z11 is one of these random variables with generating function PS. Okay, and so in this picture the number of individuals at time 1 is 3, 1, 2, 3. So that's the number of individuals at time 1. Okay, and that's because this one individual initially decided to have 3 offsprings between time 0 and time 1. Now between time 1 and time 2, all of these individuals, all of these amoeba, will decide to have some number of offsprings, and some of them might decide to have 0 offsprings. That's absolutely fine. And so in this picture, Z2 is again 3, because there are 3 survivals at time 2. That's again the number of individuals at time 2. Why is it 2? Because one of the amoeba decided to have 2 offsprings, the other decided to have just 1, and the third one just died without any offsprings. So that's a total of 3 amoeba. And this is how the process goes on. So maybe I have 6 at time 3, and so on and so on. And in general, if I want to calculate the number of offsprings at time n, then what I need to consider is all the individuals at time n minus 1, and I want to look at all the offsprings that those individuals have. Now these individuals have exactly the z and j numbers of offsprings. So this one here will have z of 2, 1, this one will have z of 2, 2, and this one z of 2, 3 offsprings. So in this picture, if I want to see what's going on with these z's, then I would say that in that level here, z of 2, 1 is 2, this 2 here. Z of 2, 2 is 1, this one here. And Z of 2, 3 is 0, because this amoeba didn't have any offsprings. And these random variables, so there are two things to notice. The first index 2 tells me that we're going up to time 2. So that we're using these independent offspring distributions for going up from time 1 to time 2. And I have 3 of these indices, 1, 2, 3 for the second index j, because I had 3 individuals at time 1. And in general, if I want to find out the number of offsprings, I need to add all these up. So the way to get Z2 is that Z2 equals 3 came as Z21 plus Z22 plus Z23. And again, this 3 is Z1. So in general, if I want to find out the number of amoeba at time n, then what I need to do is look at the number of offsprings for the first individual at time n plus 1, n minus 1, the number of offsprings for the second individual at time n minus 1, and I have to go up all the way to the total number of individuals at time n minus 1, which is Zn minus 1. Okay, so if you carefully consider n equals to 2, that's exactly what happened here. This 3 is Z1, and I have Z21, Z22, Z23, where this 3 is Z1, so that's exactly the same formula as we have here. Okay, so why is this nice and why is this interesting? Because this is exactly a random number of summons, exactly the way we covered it in the previous videos. We have Zn minus 1 many independent z's of generating function p, and because Zn minus 1 depends on these IID random variables up to the first index n minus 1, and here I have first index n, this line here, so these random variables here are completely independent of Zn minus 1, which depends only of these guys up to time n minus 1. So we have all the settings we need. We have IID random variables summed up to a random non-negative integer, which itself is independent of my IID random variables at time n, because these things can only depend up to time n minus 1. So we have the independence property which we need. And that implies that the generating function of this random sum, as discussed before, is going to be the generating function of how many variables I'm ending up. Well, this is how many I'm ending up. Z of n minus 1 many are added up of the generating function of all the individual Z and J's, which is supposed to be this P there. So this many random variables are added up, each of generating function P, and so the generating function at time n is going to be the composition of the generating function at time n minus 1 and the independent offspring distributions generating function. But of course I can keep going, and I could say is the generating function at time n minus 2, generating function at time n minus 2 at the generating function of S, except that I don't have S, I have PS. So I can apply, to calculate this generating function, I can apply the same principle. I need to go one back in time, and I have to do a composition with P, but I already had a composition before, so now I have a double composition with P. And I can keep going. I can do this actually n times and arrive to P of naught, P of Z naught, of P of P of dot 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 P of S. And in here I have a total of n-fold composition. This is an n-fold composition of the individual generating functions P of S. Okay. It's clear that I can do this because, for example, if n was 2, then P of Z2 would be P of Z0 of P of S, and that's when I have two-fold convolution. So if you look at how many times I need to do this step, then this works out. Now Z0 is 1. It's always 1. Z0 is not random. I always assume that I start with one individual. So the generating function for 1, P of Z0 of S is expectation of S to the Z0, but Z0 is 1. So it's expectation of S, but actually there is nothing random in S. So it's just S itself. In other words, the generating function for Z0 is the identity function. And if I plug that in here, then I can proceed with this line as just the identity of the n-fold composition of P of S. And that's just a notation for the n-fold composition of P of S. It's just the same thing, P of P of P of and so on S n times. Okay? So that's the generating function of the number of individuals at time n is just the n-fold composition of the individual offspring generating functions. There is one interesting feature which you can straight away deduce from this. If you look at this random sum formula, then you find that the expectation of Zn is going to be the expectation of Zn minus 1, because this is how many random variables we take, times m, where m is defined to be the expectation of Z and J, the expected number of offsprings. And again, you can do this n times. You can say that the expectation of Zn minus 1 is m times the expectation of Zn minus 2, and so on and so on, and eventually get to m to the nth power. So the expected number of individuals at time n is the individual offspring distribution's mean, which is m, to the nth power. Okay? And again, so m is defined to be the expectation of Z and J. One thing that you can immediately conclude from this is that if you want to find out the probability that Zn is not 0, that's the probability that Zn is at least 1, because it's an integer, non-negative integer. It's non-zero if and only if it's at least 1. And here you can apply a Markov's inequality. For non-negative integers, Markov's inequality applies to say that this is the smaller than or equal than the expectation of Zn over this bound 1. And the expectation of Zn is m to the n. So if m is smaller than 1, if the mean offspring number is smaller than 1, then this goes exponentially fast to 0. So if m is smaller than 1, then exponentially fast the survival probability of this process is going to be 0. So there is a very fast extinction if there is not at least one individual on average per amoeba, which is quite natural and quite plausible, and that's what's happening. We're going to explore this a little bit more in the next videos.